So continuing with the videos and thinking about perfect powers, we've seen an example. This is straight out of Barry Mazur's paper of an equation. There's 4 solutions, and 3 of them were not too hard to guess, and then one of them is just out of the blue. How would you ever guess that? Well, that's definitely tricky. Okay, so let's look at the general problem a little bit. So there's like 5 things that are variables here in principle in this kind of equation. So let's think about a couple of variations. So you can fix a k, like we fixed 24 in this example. Okay, then there's 2 natural choices. You can ask for solutions for fixed powers. This is what we were doing here. We just said 2 and 3 are of interest to us. We just want to find the solutions for 2 and 3. Okay, not any other powers. We could also have looked for any possible powers. We could have said, what if this were an m and this were an n, and those can be anything we want. So are there any other pairs of perfect powers that differ by 24? That's a much broader question and could be much, much harder and could, in principle, have a lot more solutions and, of course, could have an infinite number of solutions. Okay. Now, a little bit about what's known. In 1929, Siegel, apparently following important work of Thew, it says for fixed powers and a fixed shift. So the m and the n and the k are fixed, very much like the example we were just doing. Let me put those back as fixed powers. Okay, you can be whatever you want, but you fix them, and you say, okay, let's look at maybe like 17th powers and 12th powers that are differing by 101. Okay, that's our equation. Then the Siegel result is there at most a finite number of integer solutions to that. Okay, so that's already a very, very big result. That's exactly the kind of qualitative result you'd like to start with in mathematics. It's a big, big deal, even though you might want to go further than that. Okay. In particular, though, it doesn't give any hint of how you know you're done in finding solutions. Okay, so suppose we knew this result in advance of trying to find these solutions. We found these 3, and we know there's only a finite number to be found, but it doesn't tell us how many, and it doesn't tell us where to stop. Okay, suppose we had done a brute force search. Maybe you did this at my implicit urging in the last video. You paused it, fired up the computer, wrote a little program, and you said, oh, I'm only going to go up to y equals 8,000 on this search. And then if I can't find anything up to there, then it's certainly done. Because look at these. I've got these 3 solutions that are all double digits at most, and I'm going to go up to 8,000, and then I'll say, okay, that's it. Well, you would have missed one. Okay, so unfortunately, the Siegel result isn't an effective bound or an effective method of being sure that you're done in any practical sense. Okay, but still, it's a very big result. Okay, so let's make it even a little bit more special. Let's fix k to be 1. So, but now we're going to let m and n float. So this is different from the Siegel result. We're going to look at any powers. Any pair of power combinations, any 2 consecutive perfect powers. That's what we're looking at. Can you find 2 consecutive perfect powers? Okay, and there's more than one solution, although you could easily claim that some of them are a little bit trivial. So this is another good place to pause the video. I'm going to take my little reveal away here. Okay, so before I tell you what the answers are, could there be finitely many solutions? Well, could there be solutions? So for each particular choice of powers in this equation, Siegel says there's only a finite number. Okay, but since the m and the n are free to float, I can look at any power pair, any exponent pair. Maybe there's an infinite number in total. Okay. Well, in 1976, there was a result that says that there's actually just a finite number of solutions total for all choices of m and n. That was a big deal. Because it's way beyond the Siegel result, although again it's only for this very special case where you shift the power sequences by 1 and you're looking at consecutive perfect powers. Okay, so this is that there's a finite number of consecutive perfect powers, period, even though the powers could be as big as you could possibly imagine. That's pretty cool. Okay, well, way back when in 1844, Catalan, I think it's the same Catalan of the famous Catalan numbers in combinatorics, he conjectured that, okay, so hopefully you found this one, especially given the title of the videos, that 8 and 9 is the only non-trivial pair. Of course, 0 and 1 are obviously consecutive perfect powers, but let's not worry about, that's not very interesting. Okay, let's say pair with x and y positive integers. And so his conjecture was, I've thought a lot about numbers. I've thought a lot about perfect powers, presumably. All I can find is 8 and 9, 2 cubed and 3 squared, and those are the only ones that seem to be consecutive. Okay, and of course, we're not asking them to match exactly. That we found that the fundamental theorem of algebra answers when that happens very easily. But what about when they're one off? And I just find this a really wonderful conjecture. And the best thing is, you'll see here, is that it's one of these great cases where it's a simple conjecture. I can discuss this with my elementary school kids, and it's only in 2002 that there's a proof of this. This is one of the few things I didn't get out of Barry Mazur's paper, because it actually predates this proof. He talks about this result, but he didn't yet know about this result. Just a little tiny bit over a decade old, that we've finally figured out that, yep, that's it. 8 and 9, the only consecutive perfect powers. That's a very simple, cool thing to say about 8 and 9. Very good cocktail party conversation. The only non-trivial consecutive perfect powers. So that really answers the question for k equals 1. Wow, that's it. That's really I don't know how much more to say there is than that. Such an amazingly great result. But what about if k is bigger? Okay, what if you go back to like 24, like we talked about x squared y cubed and then 24. Assuming we knew how to prove that this is really it. This is the full list for that equation with 24 and 2 and 3. What about if we let these exponents float? Okay, what if we look at, well, how many solutions are there total? Is there a finite number total? We don't know. How many solutions are there for any particular pair of exponents, like 17 and 19? Hard stuff. Okay. But if you only cared about what's special about 8 and 9, this is a fine place to stop with the videos. But I wanted to go on because I wanted to talk about how this leads to what's called the ABC conjecture, which is something that's been getting a fair amount of press lately. Okay. Yeah, let me put that in another part, though.